probably your last session of the day, so we're going to try to make it not only informative, but fun. In order to tailor the content, we'd love to hear who of you are IT pros? If you can just raise your hand. And who of you are data scientists? And how about developers? Great, we have a mix of everything. Well, you are in the right place. We are going to be talking both to IoT developers as well as cloud developers, IT pros managing the resources for data scientists, as well as deploying the services that are created with AI. We're basically going to cover 4 different things. We're going to give you a brief introduction to Azure Machine Learning. Hopefully you have seen one of them. Actually, if you can raise your hand if you've seen an Azure Machine Learning talk already. Great. So there's not that much that I have to introduce, so we'll try to breeze through that. Then we'll talk about how you manage and deploy AI models using Azure Machine Learning. We'll talk about how you can increase the performance of these systems by leveraging hardware acceleration, both on the cloud and on the edge. And then we'll do some deployments to the edge itself. If you've seen the talk by Scott Guthrie, you probably saw an example of what Shell was able to do. So we'll try to build something similar to a slightly different target. So as you know from Azure Machine Learning, there's 3 stages into the pipeline. You can prepare your data. You can build and train a model using Azure Machine Learning. And then you can deploy it. If you made it all the way to this session, congratulations, you're at the end. We're about to deploy the services that you've been creating, first as models, wrangling that data, and now as a service. Many of you might ask, what is really Azure Machine Learning? Is it an installable product? Is it an API? Azure Machine Learning is actually a service. So that's why it's called Azure Machine Learning Services. There are several AI services that Microsoft provides. We provide you with pre-built services, which is the cognitive services, conversational AI, which is the bot services, and custom AI, which is Azure Machine Learning. Anytime that you are creating or customizing AI modules, you are in our wheelhouse. So Azure Machine Learning is a service on top of the infrastructure that you probably already use. We leverage for data, we leverage Cosmos DB, Azure Data Lake. For compute, we leverage DSVM, Batch AI, we integrate with Databricks, and of course, we use Azure IoT Edge. And all of that is running on top of the common infrastructure. We also provide you tools that will allow you to interact with our services, or if you're a developer, to create applications or services to deploy. We give you an extension for Visual Studio and Visual Studio Code that we call Visual Studio Tools for AI. And we also have a version for the citizen data scientists, which is Azure ML Studio. That is a different product. It's targeted to a different audience that can leverage the services. But we're going to be talking about the services in general, Azure Machine Learning services. And we also give you an SDK, a CLI, and a web UX for the services. We will support, and you know that we support through the platform, deep learning frameworks of all types, and we are very amicable to open source, and we're able to deploy, both help you train and deploy networks that have been created not only with Microsoft tools, but also with TensorFlow, with PyTorch, and we have made substantial investments to enable you to create models in one platform and be able to execute it in different environments by using Onyx. All of that is probably just a recap of what you have heard. One takeaway from this slide, Azure Machine Learning is a set of services that you can access through an API, an SDK, the web UX, or tools and plugins. So we're going to go and use those to perform different tasks. In addition, Azure Machine Learning Services uses the infrastructure that you already know. So hopefully for my friends, the IT pros, this is making your life easier, making it easier for you to configure those clusters that your data scientists need, making it for you easier to deploy those models to the edge and monitor them and operationalize them. So let's talk about model management. You've probably heard that Azure Machine Learning allows you to create these models. Models are basically components that are able to make predictions based on data that goes inside of them. Now, each of these models has to be run inside of an environment, and that environment is what we capture in a Docker container. So the currency of deployment right now, it's a Docker container. That Docker container can be leveraged both for deployment into Azure Kubernetes services, Azure Batch, Azure IoT Edge. But in addition, we make that container accessible to you so you can download it and run it wherever Docker runs. So if you want to run it on-prem, you can do that. If you want to take it to an edge device, you could do that. The whole pipeline is designed to give you flexibility and openness throughout the process. So let's talk a little bit more about the pipeline. As I mentioned, at the beginning is the models. And you have three sources, broad sources of models. If you're working with Microsoft, you've probably seen cognitive services. You can now customize some of those cognitive services and take them for deployment. A clear example is customvision.ai that allows you to train an image classifier and an object detector that you can then export into Azure Machine Learning and deploy. You might have a data science team in-house that has created models, and that's what we refer to by Azure Machine Learning experimentation. They use our platform to create the models. Or you might have created the models externally. You might also have purchased these models. Either way, the models are available to you as a developer or an IT pro for deployment. So what is the pipeline? Any model, whether it comes from cognitive services built by your own data scientists or external, goes into the Azure Machine Learning model registry. It's a registry for all of your AI assets. Once you have a model, you're going to have a scoring file, which is basically the application that uses that model. Both of them together are packaged along with any dependencies required to run this model into a Docker image. That Docker image can be deployed to the cloud, the heavy edge, and the light edge. We'll give you more details about what we mean by that differentiation of the edge. When we deploy, we incorporate both logging and monitoring for the service, if you are deploying a service, or a library that you can leverage to capture data from your models as they are executing, and that is the information that we retrieve back into the cloud. Basically, we're trying to close this loop. You procure a model. From that model, you move on to go and register that model into Azure Machine Learning. You create an application or a scoring script. You build an image for it. That image gets deployed, and then it's monitored. When you discover that there are any malfunctions or there's any model decay or the data is significantly different than what you expected, you can go back and retrain. So that's the virtuous cycle that we're trying to close here. There's a lot of sweat and tears that go into making that model. Actually deploying and running it at a scale, it's also hard. It's been particularly hard because if you're an IT pro, probably you're not all that familiar with all the dependencies, the environments, all these frameworks that you need to now wrangle in order to deploy a model. We're hoping to help you with that by abstracting that challenge from you. And hopefully, by the end of the talk, you will agree that we have a compelling solution. Part of the challenge of managing these models and being able to deploy AI applications is that if there is a mistake, if there is an inference that's incorrect at any point in the pipeline, later when it's deployed, the first question that you as a developer or you as an IT pro are going to be asked is, how did this happen? What is the image that was used to do this? This drone crashed. That car didn't brake on time. What happened in Tesla? We want to see what is the model that was used that made this mistake. That is why we incorporate this pipeline. Through the pipeline, you're able to always maintain a very accurate track of, in any particular application, which image was used, what files were part of that image, what application was used to inference the model, what model was used, and finally, if you trained on our platform, what data was used to train that model. This allows for accountability and lineage of any application and service that you deploy, and we maintain all of that in the cloud for you. Now, if you have been following us, you probably know that this is a refresh that we're announcing. It's a public preview refresh. So what has changed? What have we learned in all of these months of being on public refresh? First, we are deprecating the Azure Machine Learning Workbench. It was an interesting try. It was really just another interface to use the services. It ended up confusing more than helping. So we're taking it out, giving you direct and complete access to the services, either from the web, so you have to install, you don't have anything to install, or directly from the platform of your choice. If you're a data scientist, from Jupyter Notebooks. If you're a developer, from Visual Studio. If you are an IT pro, from Azure DevOps. And we'll see how that increases the power and reach of the platform soon. We have now also improved support for multiple compute targets. We will see today deployments to Azure Container Instances, directly to Kubernetes clusters, and also to the edge. We are also incorporating more models for FPGA, meaning that you can accelerate now more types of challenging models in the cloud and in the edge very soon. And we have incorporated the improvements that we have made for optimization of models into the Vision AI Developer Kit that we announced at Build and that you can soon begin to order. When you deploy our services, as I mentioned, you have the ability to deploy to the cloud, to the heavy edge, or to the light edge. Now you see those colored dots, or well, those filled or empty dots right under the different devices. They are directly associated with how much inferencing and training is possible in each of those. As you can see, the smaller the device, the less the power of the device to be able to perform inferences and training. Nevertheless, you can optimize your models and make them accurate to run on those different platforms. And because you are using Azure Machine Learning to deploy to them, they can easily scale out and communicate with other parts of your infrastructure. You might be running locally in a small camera, pass it along to a gateway running on the same building, and if you need even more computational resources, you pass it to the cloud. You can use the same model and adapt it to run on the cloud with a ton of resources, run on the heavy edge on-prem, or really nimble in one of these devices. So how do we characterize the systems? Most of us have been working traditionally on the cloud, so we are very much used to using the virtual machines, using AKS, using batch AI, using CPUs, GPUs, and now FPGAs. But as we move on-prem with Azure Stack and Databox Edge, we're beginning to introduce these other SKUs of Azure-supported hardware that is able to inference and in some cases train as well. As we get closer to the sensors themselves, devices and computational resources become smaller. So you end up having gateways that are aggregating them. And finally, on the light edge, you're running on mobile phones, you're running on IP cameras, you're even running on appliances, refrigerators and the like. Before, you had to have a different platform to access and target each of them. We are creating a platform that allows you to monitor your AI investments wherever they reside, whether they're in the cloud or on the light edge. That's a lot of talking. How about a demo? So what I'm going to show you is the portal. Now, the portal itself, it is, let me see if I can switch this. Switch to. There we go. So what you're seeing right now, it's the workspace. So you haven't. This is the Azure Machine Learning workspace. The Azure Machine Learning workspace is the web UX interface to our services. You can, of course, learn more about it and start using it directly. But let's look at the resources. As an IT pro, you probably are not only responsible for managing the compute for deployments, but also for training. So we keep a track of all the experiments run on the platform, and these were discussed in detail in the experimentation talk that I encourage you to look at if you're more interested to understand how the models are built. But we also have a compute layer where we are accounting for all of the computational resources that you currently have. Yes? Yes, definitely. How about that? Sure. When you are in compute, you're looking at all of the resources that are used, whether it is for training, for your data scientists to be able to do experiments, or for inferencing, which is, in this case, a Kubernetes cluster for deployment. You can easily add computational resources directly from the cloud. So I'm going to call this one Test Ignite. And you can decide what type of computational resource. You can just go with a virtual machine. If you have a customer that's looking to just do a small set of training runs, you can do batch. If you want to a lot of computational power, you can go for a Kubernetes clusters for deployment. So I'm going to do, actually, let me just do a virtual machine, because we're going to be creating. You get to pick which region you want to deploy on. You get to pick which size of virtual machine you want to create. So let's say I'm going to create this one. And then the compute is just created and added to your platform. Now, as you're adding the compute, you can decide which models are going to be allocated and deployed into this particular compute, like we're creating this virtual machine, for instance, or we have a Kubernetes clusters. These are all the models that have trained. Every time that an experiment is finished and the data scientist believes it's ready, it will register that model into this registry. You can also register the model yourself. You can just add a model. Let's say you found one interesting one on the internet, or you are coming from our gallery. You can just add your own model as well to the platform. Whenever you have a model, you can go ahead and choose one of those models and deploy it. Now, in order to deploy it, you need to create an image. The image is going to be able to capture all the information that is necessary to run that model. You can tag it so that in the case of a very large corporation, you might have hundreds or thousands of these images that you deploy to different targets. You get to decide what type of runtime. You can do Python or Python Spark. We're just going to do as a regular Python. You get to decide whether you want to use GPU or not during your deployment. And then you provided a scoring file. Now, you can do that scoring file. You can create that scoring file directly from your own platform, or you can do that on Visual Studio Code, or you can have created, you may have created that Visual Studio, that script file, you might have created it somewhere else. As long as you have a scoring file, you can provide it to us. Then you get to decide dependencies if you wanted to provide a dependency, for instance. You get to provide a Conda file if you wanted to customize your Conda. If you wanted a Docker file, if you wanted to customize your Docker creation. You can provide a schema file if you have a particular service in mind. So I'm just going to provide some dependencies here. You can add also your own personal files. Let's say you have dependencies on binaries. That you're using a binary that is not pip installable, that cannot be installed on Python. You can also add those files. They will be being placed inside of your Docker container. When you have created this image, the image itself, let me see. Oh, sorry. At least we have. So the image will now be created. When the images are created, you have a list of images. And you can see that the images are being created here. Here's the test image that we just created. And then you can decide to deploy one of these images. Like when you deploy one of these images, you're actually looking to deploy it to a particular compute. So I'm going to do a test deployment right now. Test image deployment. You can put any tag that you want, and you get to decide which compute. Remember that we have ACI and AKS, so I'm just going to do it in an ACI deployment right now. You have advanced settings. If I were to go with AKS, I could actually select a compute resource. So I have this test cluster that I have used already. I have provisioned. And you get to enable App Insights diagnostics. You can do model data collection if you wanted to retrain. You can do authentication if you wanted to protect your service and your endpoint. And of course, you can set the auto-scaling functions for that cluster, either automatic or static. And in this case, I'm going to go for automatic. And then the deployment will get created. Now, once the deployments succeed, you will actually have the deployments listed here. Now, every deployment you're able to inspect. In this case, you can go into this ACI service and check, OK, this particular deployment was used on which model, which image did it use, and then you can go into the details around them. You will notice that there are versions associated with all of our different models. Like in this case, I'm on version 5. We keep track of the different versions, both of your models and your images, so that we can update your deployments later on. We just finished our deployment, for instance, and you have your first service then running. There you go. The idea is that you're able to track all the activities associated with the creation and deployment of these AI solutions from this single platform. You have a single point of control and a single pane of glass for all of the activities in the system. Of course, you can do all of these also from DevOps. So DevOps for AI that you're seeing here, it's using Azure DevOps and allows you to create pipelines for deployment. Most people will do these deployments over and over again. So you can actually use our CLI in order to make those deployments, in order to test them in a smaller deployments, and then go to a much larger deployment on AKS. So you can see each and every one of these steps is just leveraging CLI commands. And you can create these commands, and you can execute any of these commands at any point. So in this context, I'm just going to try this one. And you will see that when I create the release, I actually get to decide whether I will automatically go to an AKS or not. In this context, I'm just going to run a test directly to ACI. All of the assets that are being created by your pipeline are also being captured here. So every particular component is being captured here. You see this DevOps for AI. We are continuing to increase the version. The next version will come and turn it into version 3, and so on and so forth. So you can do it from the web. You can do it from DevOps, from AI. You can, of course, take each and every one of these components and individually run them if you wanted to do that. And you can, of course, monitor all the different activities that are taking place right here. So you're seeing this installing right now the Azure ML extensions. It's going to create the image. It's going to create the service. All of these steps are accessible through the regular CLI anywhere in the platform as well. Now, going back to our component, while all those deployments are running, let me transfer to Ted, who will be telling you about how to run these models even faster.
All right, cool. Thanks, Henry. All right, great. Thanks, Henry. And so as we talk about hardware acceleration, the first thing I want to motivate is just AI in general, just some of the things that we can do with AI. And if you haven't had a chance to see the intelligent kiosk, that's something that you can see on the expo floor, or you can download from GitHub. It's a really, really fun way of just seeing some of the things that we can do with some of the cognitive services, such as this. So in this case, as you can see here, these are deep neural networks that are running, that are capturing images from my webcam, and it's able to process those images. So you can see as it's tracking my face, I'm looking to the right, then I'm looking to the left. You can see that, that it's tracking my head pose. Mouth aperture is just how big my mouth is. Eye aperture, if you think about fatigued drivers, maybe this is, late in the afternoon for you, and you're tired, and you're trying to sit through this talk, and you're just kind of going, I realize, I get it. We keep the code room so that you can stay awake. But if you'll notice here, it's actually able to catch that my eyes were closed. Right? So these deep neural networks are powerful enough to be able to catch sensitivities like that. Or maybe you're driving, or your teenager is driving, and maybe your teenager is doing something like this, and you can see distractions pop up. Right? And so what's happening in that case is that it was able to run computer vision DNNs that essentially look at the picture and describe what that picture is doing. Like somebody is holding up a cell phone, and you can take that, and then you'll be able to send an alert based on that. So why did I show that? Because those models are essentially deep neural networks. And a lot of these breakthroughs in computer vision, in translation, in speech recognition, and question answering, all of these algorithms, all of these things have been powered by these deep neural networks. And so it's been a really, really interesting space because of these algorithms. But the big problem with them is that they're challenging to serve and deploy in large-scale solutions. And you get to a point where you have to make these trade-offs. Do I want low latency but high cost and high power? Or am I able to process lots of images? And how do I serve them at scale? And so the size and complexity of these deep neural networks is really just outpacing the growth of commodity CPUs in order to be able to process all of these DNNs. So as we look at how we can accelerate these deep neural networks on this spectrum from the most flexible to the most performant. On the left, you see the CPUs, and CPUs are the workhorses of the internet where you have basically processors that can process anything. And they're great, but then they're sequential. And so speed might be something that is not as much there as in something like GPUs, which are highly parallelized. So you have something that you want to run on a GPU. A lot of gamers out there, you're probably very familiar with how GPUs are great to be able to process everything in parallel. So some of the downsides of GPUs are probably cost. Again, if you've ever tried to buy a GPU to play your favorite video game, there's the cost component. On your far right are your ASICs, your application-specific integrated circuits, and these are basically circuits which are fixed. They've been created, and then you can't change them anymore. And so Henry will talk about, in the next section, about some of the work we're doing with ASICs. But I'll talk about the things that we're doing with FPGAs. And FPGAs are field programmable gate arrays. These FPGAs are essentially chips that you can reconfigure. They have logic blocks, and they have other things in which you can rewire and to be able to take a deep neural network and to be able to configure that chip so that the circuitry of that chip is essentially running that model. And you're putting these complex algorithms directly onto the chip. So we look at these chips as a portfolio, in the sense that they're all available in the cloud. And so if you wanted to do training, we have CPUs and GPUs available to train these deep neural networks. And from an inferencing perspective, we announced that build in May, the ability to be able to then deploy models to inference on FPGAs. That's the story in the cloud. On the edge, we have a very similar story where you'll be able to retrain models locally on edge devices with CPUs and GPUs, and then inference on the edge with FPGAs and then ASICs. So one of the main advantages as we talk about Project Brainwave and the way to be able to use FPGAs is that there's no batching required. And so the concept of batching is just basically the amount of data that you need to send into a specific chip. And the way I want to illustrate this is think about your favorite car dealership. Okay, think about your favorite car dealership. And you need to take your car in for repair, and then you're driving to your car dealership, and there are 10 repair bays, right? There are 10 repair bays. So you're driving in there, and there are these repair bays, and you drive a car in there, and at each repair bay, there's a technician. The technician will need to take off the wheels, we'll need to change the brakes, we'll need to do all these various things to that car, right? But since there are 10 repair bays, if you have 10 cars, you can drive them in, each car in each repair bay. The technician is working on the repair. If it's the same repair, the technician, is taking off the wheels, it's changing out the wires, it's replacing the brake pads or whatnot, and you get this really, really nice parallelism. And then all 10 cars are repaired, all 10 cars can leave the dealer, and then you have 10 repaired cars. Super cool. Now, the great thing about that is if you have 10 cars that are ready to be repaired and 10 cars that have the same repair, drive them in, get that repair, take it out. right? And that's essentially a GPU, this highly parallel way of processing things where you have the data batched up. So you have, say, 128 images. You're sending it all to the GPU at once. The same operation is processed on the set of data. So basically, the same operation on all of the data at once, and then the next operation on all the data at once, just like what's happening in that car dealership. And then you get super high throughput in that sense. Right? So when you hear some of the numbers, the amount of throughput that you get is really, really high because of that parallelism. So what are some of the downsides? The downsides are you have 10 repair bays, you have one service technician at each one, but you only have one car to repair. So now you're sending one car to that dealership, and the rest of the service technicians are idle because of union rules or whatever, and they're idle, and they're just sitting there, and they're not able to do anything. And so you just basically are not utilizing 9 of those repair bays. So if the GPU is the car dealership that has these 10 repair bays and has really, really high throughput, the FPGA can be seen as a pit stop like this. You can imagine a car coming in, everybody swarming in, and basically trying to do everything at once as much as possible, right? And so that's what we mean by batching, where with the FPGA, you have the ability to be able to send in one image, and then the circuitry of that, the model that's been deployed there is able to process as much of it as fast as possible, and then you're able to get what we are calling essentially real-time AI. Because now you're utilizing pretty much the entire chip. You're utilizing all the resources to get you the response as fast as possible. And so that's the main differences between something like a GPU and something like an FPGA. And so by doing this on the FPGA, now you can get ultra-low latency of the data that you're trying to process. And if you have 10 images or 128 images, you can send 128 images to the GPU, or you can send, and you're sending them one by one to the FPGA. But the time it takes for the FPGA to process is so little that we're essentially trying to work towards that would be the same time as a GPU. But then you also get the benefit of very low batch sizes. And so I just want to illustrate this with this video here, where we're comparing a batch-oriented DPU and also an FPGA. So you can see here at the top, this is a DPU. This is something like a GPU. And if I were to send in a batch of 256 images, and then starting down to 128 to 64 to 32, you can see the teraflops starting to go down. Right? When I'm sending batch sizes that are smaller and smaller, my utilization of that GPU is lower and lower. Does that make sense? And so this is like your car dealership where all the repair bays are not being utilized, right? Because you're sending in smaller batch sizes. Now, if you look at an FPGA and the ability to run things on an FPGA, let's see what happens there. With the FPGA, regardless of the batch size, when we say 256, we're essentially sending one image at a time, except just 256 images. You're utilizing the entire FPGA. Right? This is your pit crew swarming all at once, trying to get that car repaired as fast as possible. So super high utilization regardless of batch size. And that's one of the main advantages of the FPGA. So as we talk about deep learning on FPGAs, that's where we talk about that performance. Excellent inference at low batch sizes. And now the question is, when will you have these scenarios? If you think about the times in which you only have one image and you need to try to get a result from that image as soon as possible, think about a manufacturing line. You have a camera on the manufacturing line, you're trying to take pictures of assembly line products, and you're trying to predict whether there's a manufacturing defect or not. You're taking one frame at a time, sending it, and trying to get a response back, right? Or security video, or any other types of applications where one image is coming in at a time. So in this case, FPGAs would give you an advantage because then you can process that and get a response back as part of your pipeline. And again, from a portfolio of chips, if you have a billion images that you're just trying to chug through as soon as possible, GPUs are available for those high throughput scenarios. The other thing about FPGAs is in terms of flexibility. You think about the fast changing landscape of AI today, where if you wanted to design a chip and you wanted to harden it onto an ASIC, that process to be able to test it, fab it, manufacture it, and to be able to get that into the data center or wherever you're trying to get it into could be about a 1.5 or 2 year process and tens of millions of dollars. And that's some of the downsides of fabbing your own chip. But with an FPGA, you're essentially designing circuitry and software, and then you are just flashing that FPGA with the design in just an order, like flashing the FPGA would just be in an order of minutes, and now you have this completely new circuitry that then you can use to run whatever algorithm that you have. And so with AI changing so rapidly, with new types of calculations and algorithms and just ways of optimizing things coming up, having this flexibility is another one of the main reasons that we're using FPGAs. Microsoft, we've also worked on algorithms to be able to take advantage of the data types so that we can exploit some of this sparsity and the deep compression so that we're able to get the same similar kind of performance on an FPGA as you get with full fidelity float 32. In terms of scale, we have the world's largest investment in FPGAs. Right now, the service is available to you as the end user, that you're able to deploy models directly onto the FPGAs. But we've been using FPGAs for a long time. And these FPGAs have been powering accelerated networking. If you ever provisioned a VM on Azure and you had the option to select accelerated networking, this is all powered by these FPGAs. A lot of the Bing queries are also powered by FPGAs. And so you think about the ability to be able to take in a query, to be able to process that, to be able to give you a response super fast. That's also being done on FPGAs. And so this is something in terms of the production pipeline, in terms of just the ability to be able to get FPGAs into the data center and to be able to make them available is something that we've been doing for quite a few years. From a cost perspective, in terms of pricing, to inference 1 million images, the pricing is at 21 cents, meaning that you provision your service and you have 1 million images, and you're going to send them to the FPGA for inferencing, about 21 cents. And so I'll leave that as an exercise to the user to spin up your favorite GPU and just to get an idea of how much it would cost to be able to inference 1 million images at batch size 1. So Project Brainwave is a scalable FPGA-powered DNN serving platform in which we're able to provide that ultra low latency, the high throughput serving DNN at these low batch sizes. And because of that flexibility, we're trying to be future-proof so that we can always give you the latest and greatest, and then we're able to keep up with a fast-moving AI landscape. And then today, in terms of what we do in Bing, the ability to be able to deploy TensorFlow and cognitive toolkit models, what's available on the public cloud is the ability to be able to deploy TensorFlow models. But basically, the idea of taking those pre-trained models and to be able to scale it out onto the cluster of FPGAs and then to be able to run them on that. And what we're announcing is that we are providing some new models that you'll be able to deploy onto the FPGAs. In addition to ResNet 50, we also have available ResNet 152, DenseNet 121, VGG 16, and SSD VGG. And also the ability to be able to customize those weights. So if you've ever played with deep neural networks before, you're probably familiar with the millions of parameters and weights that are there. And so today, in May, in Build, we announced the availability of ResNet 50 on an FPGA with a pre-trained on the ImageNet data set. And so you couldn't do anything about the weights. You could use transfer learning and be able to train a classifier to be able to do that, but then you couldn't do anything. But now you can take these DNNs and also retrain and fine-tune so that these set of weights will be able to give you better accuracy. And so if you want to sign up, we have a quota request form. So just go to this website and the Git repo, and it'll walk you through the process of being able to fill out the quota request form so that you could try it out on your own. So now I'm going to jump to the demo portion of the talk, and I'm going to preface the demo with with basically the types of demos that you might be used to seeing. A lot of demos might go on for minutes and minutes, and it's cool, but AI is moving very fast. It's going to be like Thursday night when you're going to Universal Studios and you wait an hour and a half in the Harry Potter line and the ride's over in like 30 seconds, right? So because everything's running so fast, I'm going to show a demo and then it's going to be over. So I just want to give you a heads up that that's what's going to happen. And so what I'm going to do here, while I'm setting this up real fast, is also to talk about what we're doing in the demo. So this is ResNet 152. ResNet 152 is a much more complex algorithm. It's a larger algorithm than ResNet 50. ResNet 50 had 8 billion calculations. ResNet 152 is close to about 22 billion calculations. And one of the downsides of these very complex algorithms is that you may not want to use them just because of the time that it takes to run. You're thinking, maybe a typical data scientist might be thinking, okay, I'm going to use this algorithm. I like it. It gives me some good, performance. But then the big problem is I can't use it. Going back to that problem, I'm trying to serve it on CPUs or GPUs, and then I'm not getting that cost and performance benefit. So what we have here, what I'm going to show you. Let me just bring this over. Right now, this is a Jupyter Notebook, and again, to the data scientists out there who like to use Jupyter Notebooks and Python SDKs, you can also do this in something like VS Code or PyCharm. But the idea here is we want to meet you where you are in the tools that you're already using. This Jupyter Notebook is available in our sample notebook, so you can just clone the Git repo and be able to see this. But what I've done is essentially bring up the load up the ResNet 152 model, and then I trained it on the cats and dogs data set, and then I fine-tuned it because this is the quantized version of that model. After fine-tuning, then I'm able to get a lot better accuracy. And then now the model has been deployed. It's exposed as an API, and now I can send data to it, okay? So you just waited an hour and a half for this ride, okay? So the ride's coming up, okay? So basically what I'm doing now is I'm going to send images to the FPGA and get a response back. And you can see, essentially, immediately, what's happening is I have these pictures. I'm sending them to the API. The time that it takes for this picture to get off this box, to travel to the API, to be processed, to be converted, run through the 22 billion calculations of ResNet 154, and to be able to send that response back is about 12 seconds, 12 milliseconds. And what I had showed in the previous slide was the Stanford group doing it on a P100 GPU. The fastest that they were able to get it was about 22 milliseconds. And so you can see how much better the performance is when you're doing it on an FPGA at batch size 1. And so this is really how we're enabling you to be able to go towards real-time AI in a way that is super performant and also very, very cost-effective. And so with that, I'll turn it back to Henry to talk about the work that we're doing on the edge.
Thanks, Ted. Hopefully, you'll get a little bit more time with the Harry Potter ride. Highly recommend it. I actually got to spend half an hour on it because it broke when I was there. Not very nice. Those spiders are not that fun when you're looking at them for half an hour. Anyway, just to go back to our presentation, remember that we had started the deployment with the DevOps for AI, so that actually succeeded. So you can actually look at all of the independent steps. We did, as you remember, we register the model, we create the images, we create a service, and we deploy them. You can still see all of those assets being created here. There's the deployment, there's the image that was created, and there's the new version of that model that we have created. So this is a good way to manage all of your assets in the cloud, but could we do the edge? Now, the edge is an interesting beast because more and more we're seeing people wanting to deploy to the edge. Why do people want to deploy to the edge? There are many reasons. Sometimes it's just business agility and scalability. The ability to have unlimited computing power available on demand is what the cloud provides you, but you sometimes don't care about that much amount of power. You care about latency. You care about braking in that car in that those few milliseconds. You care about that drone not hitting that person. You care about detecting an oil spill. You care about stopping the production line immediately before a part passes by. In some cases, you might have privacy concerns. You don't want to send your images to the cloud. You just want to do those identifications or those classifications locally. In others, you might not have connectivity. You might be in the middle of the desert. You might be running underground. You might be in a submarine. There are many reasons why you would want to run on the edge. Now, before the explosion of deep neural networks, it was really hard to target the edge because you have to implement these massive mathematical operations into these very small processors. So that's the top portion of that diagram. You can see very little processing was happening on the edge, and it was very specific. You needed to have connectivity. The neural processor units are actually accelerating the mathematical operations that make it possible to compute and inference these models. You saw it with an FPGA. You saw how fast it is. We can't really put an FPGA in a camera like the one that we have here on the floor that I'll show you in a second. But we can put really small systems on a chip. So several of the hardware manufacturers have started to address the challenges on running on the edge. There's reduced compute power because they have to run these low compute processors. Now, you could try to use GPUs, but they're very small GPUs, and there's a fragmentation, and there's not a common abstraction for them. There's nothing like DirectX for GPUs in phones or in IoT devices. The alternative is then to be able to introduce neural network accelerators. Now, as we all know in our industry, we like to do the same thing many times. So we have several solutions for neural network acceleration. So if you're trying to deliver neural network accelerated models to the edge today, you have to understand specifically the hardware that you're targeting. And this is just the best known. There's tons of hardware manufacturers. So how can we address it? As you recall from other talks probably, and I briefly mentioned it, an open neural network exchange format like ONNX allows you to train wherever and capture that model in a format that can be passed along to different inferencing engines. The same concept can be applied if the engine itself is aware of the hardware. Now, there's a translation because you trained on the cloud, you trained with all of those resources, and now you have to run in this small device. Traditionally, that meant a lot of C++ and assembler and a bunch of hardware engineers for months or years to try to get your model to perform. But these companies have started to partner with Microsoft to create an abstraction that allows to translate those models to their hardware-specific solutions. So if you recall what I told you about the pipeline, you start with a network. Ted showed you how you can use images to train that network. You can generate a model. You add that file, and then you deploy. And you can deploy to the edge into split deployments or in a consolidated deployment. So the next slide is an eyeful, but hopefully we can talk through it because we've seen it. All the steps that we have worked in the past, right? So when you went through training, you might have started with a model that came from a gallery. There are certain models that you can use and translate for the edge. There are others that will not translate. They're just too big. Genome folding is probably not going to happen in a small device for a long time. But being able to understand whether there's an empty spot, whether somebody is stealing something, or what did you pick up before you went to the cashier, it's something that can probably be done on the edge. Those type of models can then be deployed to the edge. We have a gallery that allows you to identify what are those models. Then you have to train it, because it'll be unlikely that it happens to be that the one model we have actually works for you. We have now tools that allow you to train that by just providing images. Let's say you want to use the image classifier and actually classify your own apparel items if you are in a shopping store. If you might want to use it to detect your own anomalies. Maybe you are manufacturing toy cars and you want to detect a particular type of anomaly. You just need examples of those images, and you retrain it. Now, as we saw in all the other demos, once you have those models, they go into our model registry. And that's where the magic begins. Because since we know how you train that model, and we understand the dependencies of that model, we can translate that model. So you can tell us, oh, I want to target this Qualcomm device. And I'm going to show you a demo of how you do that with a Vision AI dev kit soon. Oh, I can actually go to the heavy edge, and you can see a proof of concept of that on the Intel booth, where they are using Azure Machine Learning to deploy to a heavier edge. What we do in turn is we take that model, we will translate it, we, of course, store the resulting model, we build that image, we know what needs to go into the image because we help you build that model, and we deploy it. So let's go through this in a different way. So you start with a model. You might have created it. It might have come to you from cognitive services. We take that model that you have. We create an image. We deploy it. You can start with a model. You might have trained that model. You prepare and register that model. And you decide how to deploy it, and we'll deploy it. You might have trained a model. You might customize an application that uses that model. Maybe you want it to raise an alarm. Maybe you want it to stop the car. Maybe you want it to turn on the light. You just build that application. You give it to us. We package it. We deploy it. Now, really, the way that we deploy it is using Azure IoT Edge. Why? Because Azure Machine Learning, per se, doesn't manage your devices. It's a different thing to manage a server than to manage a device. In order to manage devices, we have a solution that's called Azure IoT Edge. They have great demos, and they have great sessions around that. So we just stand on the shoulders of giants and let them do the management of the devices. And those devices are then provisioned with our modules for AI. Now, once the module is inside of the device, it calls back home. It provides you information. It doesn't provide us information. It provides you information about what the model is doing. It's completely stored only in your storage account, and you get to make decisions such as, let's retrain this. It actually is not working great, or maybe I can improve it for other cases, and so on. Now, in order to make this possible, there are three components, right? You need the models. There's a bunch, and we're going to provide you some, and you can create your own. There's the platform. We have that. We're doing Azure Machine Learning and Azure IoT Edge. And then there's the device. So we didn't have a device, so now we have a device. So this is the Vision AI developer kit. This is the one that you saw in the demo for Shell. This is the one that I'm going to show you how to program and use in a second. It's going to be available for order pretty soon. I'll give you a URL towards the end of the presentation. Now, the premise of this is a developer device, right? Eventually, it's a reference design as well. So you will see hardware manufacturers releasing new hardware that is compatible with Azure Machine Learning and Azure IoT Edge that benefits from this. But developers are going to be using this platform. How are they going to use them? They're going to be using it by using pre-built solutions. They're going to be using it by just going to a browser to create those models on something like customvision.ai. They might be creating their own models on Visual Studio. They're going to come to Azure Machine Learning with them. We're going to turn them into hardware-accelerated containers, put them in Azure IoT Edge, and deploy them. So how does that really work? Let's do a demo. So for this demo, I'm going to use Visual Studio. Now, this Visual Studio code, free. You guys can take it. I have just installed the Visual Studio Code Tools for AI plugin. And as you can see, there are already some training examples. If you don't have models, if you want models, here are models. Even if you're not a data scientist, you can get started. You download any of these. You will train them directly from Visual Studio. You can also, of course, do it through our website using Jupyter Notebooks, and you create your models. There happens to be one here. Now, on your left, you'll notice this new panel. It's actually directly communicating with Azure Machine Learning. So what you can see here is that as part of this deployment, I can actually connect to the servers directly and look at all of the different spaces that are workspaces that are in there, and I have the same view that I had on the web. So you can check all the experiments that you've been running. You can check all of the compute that's available for you. You can check all of the models, and there's the models that we just created, right, including my model. You can see all of your images, and you can even see all your deployments. This is a great tool, even if you're just targeting the cloud, right? Because now as a developer, all the abstractions of these steps are available to you directly from your IDE. And you're able to do a lot of things. Of course, you can take a model, and you can build out properties. You can create an image for that model, as we have done in the past. You can also come and add compute if you wanted to do that. You can create compute directly from here. And that, if you say you wanted to train or to deploy. But more interestingly, you can actually go and deploy an image. So you can come here and deploy an image. Now, you can deploy a service from your image, or you can add it to the IoT Edge solution. This will be an IoT deployment. Now, in order for us to move into deploying into the edge, let me show you IoT Edge. I don't know if you are familiar with it, but IoT Edge basically is part of the Azure experience, and it gives you details about different devices. Here we're looking at a device. This device has particular modules, and you can, of course, add modules. When you add these modules, you need to provide it with an image. So there is a manual step to do this, but let's actually do it directly from the command line. So if you're a data scientist, you too can deploy to the edge. So as you know, you register your model. The next step is where we make use of that partnership with these hardware manufacturers. This step will translate and convert that model to Snappy, and we'll be able to then, once the conversion is done, re-register that model. So we will maintain the lineage of your model. We will know the version before we translate it and the version that we translated, because that's the one that's going to be running on your device, and you probably want to see it. The conversion takes a few seconds, as I said. The conversion is primarily taking the original model that we have suggested to you with all of the images that you used to retrain it. You created a version of that model that we now convert and register. Once the model has been converted, you can actually go ahead and get that compiled model. That model then can be part of a Docker image. So I'm going to start the creation of that Docker image there. This is the file, sorry, this is the application. Remember the scoring file. I'm just creating the scoring file. And then you can go and create the image. You will notice that there are, and you have access to this from CLI and the cloud. You get to decide what type of architecture are you targeting. Is it ARM32? What type of runtime do you want to use? So on and so forth. Now, I have already created images, so let me just use the image that I have. I'm sorry, I should have created this first. And we're going to wait for that creation to take place. While that is creating, I already have images that I have created, so I'm going to deploy them. So I'm just going to say that's the image location. These are all the different images that I have. And this is still creating the file, so let me continue here. That's creating the image. While the image creation goes on, I can actually go and deploy the image. So I'm going to deploy that image. What that is doing is it's connecting to the IoT Edge device, and it is, IoT Hub device. And in the cloud, it's telling it, this is the module that we just trained that you want to deploy into the platform. It's taking a couple of minutes. Sorry. And as you can see, it has configured all of the details for that deployment. And then now we can go here into the device details, and let's do a refresh. And that is our device. And you can see that new model, the AI classifier. It's currently being set to run and deploying to the device. So we already have the model deployed, and we want to show you this model. What you're seeing right now it's this camera. So this is Ted and I's handiwork, so please don't judge. The scenario for one of these cameras is, hey, you might have these cameras in parking lots. Now, when they are in a parking lot, one of the serious concerns is people that block the fire lane. Now, detecting something in the fire lane normally will require somebody driving around and looking, hey, somebody illegally parked, and so on. Now you can just put one of these cameras. Now, I want to pay you to pay attention to something. That camera is only connected to power, not even to power right now. It's running on batteries, and it only has the HDMI. So what you're seeing in front of that, if you pay attention to the screen, is that's the fire lane, and I'm just going to put a car in front of it. And there is a normal vehicle there. There shouldn't be a normal vehicle, so you can raise an alert. If there is a fire truck, it is a fire truck, so it's perfectly fine to be there. So thanks. So bit of a moral debate on that, on what else should we be tracking in the parking lots, but you catch the example. So you can basically have hundreds or thousands of these cameras, not just necessarily looking for fire trucks, but looking for different types of classification, different types of anomalies. You can put them in factory lines. There are multiple applications that you have for these type of technologies. So as I mentioned, these devices are available. So in order to procure one of these, you can just go to this website, visionaidevkit.com. Order one of them, register to order them, and when you have them, hopefully you can play with them, give us some feedback, and we'll try to build a better platform for AI for you guys. And with that, I think we're done. We'd love to hear some questions from you. More than happy to answer any questions you have about the platform. Yes?
Exactly, yeah. So the question was, when you get this situation where you have the feature extraction and then you have a classification step of your model, what's happening essentially on the FPGA is we're providing you headless versions of these in the sense that the final layer is not available on the FPGA. And so the FPGA is really just the feature extractor, and then you train a classifier, whatever classifier that you want, that will run essentially on CPU. So that you'll be able to do transfer learning. And so because the DNN is the long pole, once that's optimized and that's super fast, the classifier at the end running on CPU is not that big of a deal. Yeah. Mm-hmm. Yes, absolutely, absolutely. And so the North Star, the goal of where we want to go with this is to be able to enable you to bring your own models. So that right now we have highly optimized versions of these pre-trained models, but then as we're building that out, we have these operators that are used for these models, and that you can essentially bring in your own with these specific operators that then we can put together and to be able to put onto the FPGA. So I'm sorry, the performance of FPGA compared to? Oh, TPU. OK, so the question is performance of FPGA compared to TPU. Yeah, it's a very good question. And so we haven't done benchmarking specifically on the TPU, but looking at some of the publicly available websites for TPU, one of the things that was listed was that batch size 1 of ResNet 50 takes more than 10 milliseconds on a TPU, whereas on an FPGA, Microsoft Research was able to get that down to less than 2 milliseconds for ResNet 50. So that's just one comparison. Of course, TPUs are generally designed more for training of these DNNs, whereas right now we're positioning the FPGAs for inferencing, for ultra-fast inferencing.
Yes.
Oh, sorry. Go ahead. Yeah. Great question. Yeah, so from an FPGA perspective for serving, let's say you wanted to train your model on something like a GPU. You can spin up a batch AI GPU cluster, submit your job, run your job, and then spin it down, and then you're not billed anymore for that. From an inferencing perspective, when you deploy your model, you're essentially provisioning. Well, I mean, underneath the covers, we do that for you. We'll provision the FPGA VM. We'll deploy your model on that and return a gRPC API that you can use to be able to inference. And as long as that service is there, you're just charged for the time that service is available.
Yes?
Hey, can we go back one slide where you had the link up? Where you
Sure. There you go. No worries. Any other questions?
Cool. Well, thank you. We'll see you at the Harry Potter line in Universal Studios.
There you go.